All right. So let's bring in. Oh, that's what it's important. I'll bring it in here. Usually I project this beautiful manatee on the screen during the test, but I forgot. So there's a manatee, a glorious manatee. I hope you enjoyed the manatee test. And now you have to wait for test 2 to know what animal it'll be for test 2. The rule is they start with M. So, lots of options. I know, don't overthink it. There's lots of options. It's crazy. First and foremost, I'll do it in red. Hopefully you got my announcement that I sent out yesterday. So mom, which is your assignments, mom is still down. As I said, I'll do a sad face, but it's actually kind of a smiley face for you guys because just take a break. You can't do anything. I can't get in there. There's nothing I can do. And so if I can't get in there's really nothing to do. Okay, so just take a break. Should be up and running next week sometime. Once I'm back in, I'll extend all the due dates by however long it was down for, and any late passes that you've applied, right, to those ones that you weren't able to do, I'll extend those as well. Don't worry. Okay. And so you will have time to work on those assignments, but for now, take a break. You deserve it. Luckily, we already had our test, so you don't, there isn't a ton to do in there, but it's still down, and I'll send out an announcement when it's back up and running. Yeah.
When it comes back, is that going to result in us having 10 things on the go all at once?
No, because there's no assignment from the lecture today. So it'll just be what you had. So unless it's still down by Tuesday, but I really doubt that. So no, no, no. So yeah, any questions about that? I know it's really kind of nerve-wracking. You're trying to get in there. You can't. So just stay calm. Yeah. I did not finish marking your tests. As soon as I am done marking them, I'll post the grades on Moodle. I don't usually send out an announcement when I've posted the grades because I feel like I'm spamming you a lot. So just kind of check back. But over the weekend sometime, I'll post the grades whenever I'm finished. You'll have them. Okay. And so I'll put them up and get them off my desk, so to speak. And so, and then of course, I'll hand them back on Tuesday. Okay. So, all right. Anything else? No. Okay. So, chapter 5, the start of my favorite part of the course. There's a couple of kind of, some terminology and some core concepts that we need to cover today in 5.1. And then we get to start what I would call the meat and potatoes of the entire course. All right. And so far, especially up until test 1, it was a lot of kind of, and then you do this, and then probability, and then you do this, and then the binomial, and then all these kind of seemingly random things being thrown into a pile and call it a course, right? And that is kind of what's happening, kind of. Okay. Now we're going to settle down and only talk about inference. Now, inference, I'll do here. When I say inference, what do we mean That's when we use sample information, right? So a statistic, it's all in the name, right? A statistic to learn about a parameter, right? So some population information. So when we use sample information, maybe I'll do it this way. A statistic, my manatee is getting in the way here. But he has to stay on there, I think. So when we use a statistic or sample information, I shouldn't say learn, to infer, right, or learn about a parameter or population information. So we use a statistic to learn about some parameter. And there are lots of different kind of statistic parameter relationships that we could talk about. But for us in this course, we focus on just two of them. So if we have the, oops, I'll put the statistic here and the parameter here. The most common statistic that we use is for the mean, right? And we said, well, the problem with the mean, which is the average, which we know if it's from the sample, we use an X bar to denote the mean, the sample mean, right? But we also know that the problem with all these things is that there's also a population equivalent, right? Which is your mu, right? Which, okay, if we're doing inference, is when we use a statistic to learn about, I should have said the corresponding parameter, but that should be implied as well, right? And so when I use the sample mean to learn about the population mean, right? And so what we're going to do is use X bar, but really what we're trying to learn about is mu. Yeah? Because we can collect a sample, but that's kind of boring. We know everything that we could possibly want to know about the sample, right? You can just look at it, do calculations, graph it, do whatever, right? Whereas really what we're interested in is finding out about the population that it came from, right? And kind of a subgroup here, the standard deviation from the sample, we call it's an S, or as the parameter, we have our lowercase sigma. Now, we don't tend to do inference about the standard deviation in this course, but we use it to learn about mu, so, and therefore sigma. But we do use, I'll make a note here, usually we do not do inference on the standard deviation. It's still a statistic parameter relationship though. So it'd be weird for me to not put it on there. The last thing that we can commonly talk about is a proportion. Yeah? And so a sample proportion, right? We could say, okay, how many people have a black car. Right? I have a black car. 1 out of all of us, right? That's a proportion, right? And so, but that's also categorical data, right? And so for categorical data, we analyze proportions, okay? And so for proportions, what we're going to use is a P with a little hat on it, okay, to denote that it's a sample proportion. Okay? What we're trying to learn about is the population proportion. Now, this is the only time where we don't use a Greek letter for the parameter. Okay? We tend to use P, right? Or if you prefer, you can use the Greek letter pi, but pi is also a constant, right? And so it gets kind of messy and potentially confusing. So if you want to use pi, that's great. That's cool. But I'll be using a lowercase p to denote the population proportion. So what we'll have is we use the mean for numerical data. Usually we're doing inference about the mean for numerical data, and for categorical data, we do inference about the proportion. I'm gonna add, I know I'm cramming everything onto one page. Oh, how do I add some lines here? There. In terms of the layout of the next couple of chapters even, okay, because we're gonna spend a lot of time here. For chapter 5, we introduce inference. Introduction to inference. And we do that with proportions. So we're going to focus on proportions and learning all the skills around inference. Okay. And so let's see here. How can I? 5.1 is basic. It's today, and it's just kind of terminology and other things. Terminology. Okay. Basically. 5.2 is on what's called a confidence interval. Okay? And so we introduce a confidence interval. Now the confidence interval, what it does, kind of broad strokes, is it gives us a reasonable range of the values, right? We saw that last day, right, where we had some, I can't remember, 13%, right, who had said that, where is it? Is it way back here? Here. We had this example, 13% of Americans think homeschooling provides an excellent education. So they had 4 different categories to choose from. But what we did is we said, okay, if you chose excellent, I'm going to use that as a success. And then not excellent, well, that can be a failure. You can just lump them all into a kind of a not group. Okay? So then we can find the mean and the standard deviation, and using the mean and the spread, right, we were able to say, okay, well, then I can find some plausible range of values. Yeah? And so we're just going to do that, but in a slightly more concrete way for confidence intervals. But we've kind of already done it. I just didn't call it a confidence interval. Okay. And so a confidence interval, it gives a plausible range for the parameter. So like I said, we've already seen it, right? But we need to introduce some rules. In section 5.3, we introduce what's called a hypothesis test or hypothesis testing. Hypothesis testing, I would argue, is the reason you all have to take this course. Okay? Because anytime you want to prove something, right, what do you actually want to do? If you kind of thought about it this way, maybe you probably haven't, but really what you want to do is you want to assign some probability to seeing something like this, right? So if you're comparing the outcomes of two drugs, for example, kind of out there, but you've developed a new drug and it's supposed to, I don't know, help with migraines or whatever, right? Then however you measure that, you can compare the two. And then if you're able to say that, hey, the probability that these two work the same is very, very small, right? What does that mean? They work in a different way. Hopefully mine works better, right, that I've developed. Or kind of more simply, if you want to prove that you sold more, right, than your colleague, you can look at those numbers, right? How much do I sell on average? How much do they sell on average? Compare those two. If the probability of those two things being the same is very, very small, that means they're not the same, likely, right? And so that's what hypothesis testing is all about. And so really what it does is it assigns a probability to a hypothesis. A confidence interval, I'm going to abbreviate CI usually, and hypothesis test HT because it's really long to write if you don't. Okay. And how we introduce these is with one sample proportion. So you've collected one sample, you have counted how many successes, how many failures you had in your sample, right? Because it's categorical data. And then your proportion is going to be the number of successes over your total sample size, right? One black car out of all the other fun color cars, right? Plus my black car. Okay. Now, in chapter 6, we keep working on it. Inference for categorical data. Six 6.1 is just a review of confidence intervals and hypothesis testing for one sample proportion. Okay. The reason I'm outlining this is just so you can see how much time we're going to spend here because it will feel overwhelming as I introduce these things, okay? But we're gonna spend a lot of time. So each of these sections we spend a day on. Ding, 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 ding. Already we're at 4 days just on the same thing, which is a long time in a short term like ours, okay? And so we're gonna spend a lot of time here. There's a lot of rules and a lot of kind of things to keep an eye out for, okay? But there's an upside. Once we've learned those rules, right, and we know how confidence intervals work, or we've seen how hypothesis testing works, then we get to apply it to a new scenario. But all those skills stay the same, right? And so then every day we we introduce a new type of question. Okay? And so how it's going to go is 6.2 is confidence intervals and hypothesis testing for not one, but 2 sample proportions. Right? So for 2 sample proportions. Hmm. 6.3, we only do hypothesis testing because it'll be slightly different. But again, once you know how hypothesis testing works, right? And I'm not expecting you to feel comfortable with hypothesis testing after this first day. Not even here at 6.1. It's going to take us until, mid-November until we can feel really confident with hypothesis testing, okay? And so don't worry. But maybe by this point, okay, I can see it. They're all the same. Hypothesis testing for 3+ proportions. And then finally, 6.4 is hypothesis testing for a contingency table. What we're looking for specifically is whether, remember contingency tables, you had, well, what's one that oh yeah, is it the Texas or the Florida voters? I think it's the Tampa, Florida voters, and how they feel about global warming is one on your assignment, right? Everyone remembers that one. No one likes that one, but everyone remembers that one, right? Oh, that was so confusing, right? Now, once we've done 6.4, we'll be able to say with hypothesis testing whether how people voted and how they feel about global warming are in fact independent or potentially dependent on each other, right? So we'll have kind of rules for why they may be dependent or potentially independent of each other. Okay? Then we change gears in chapter 7. Chapter 7 is inference for numerical data, which is really fun because averages are just easier for us to wrap our heads around, usually. There's a reason we start with proportions. It's because we get to use the Z distribution still that we're familiar with. So it's a nice place to start. But inference for numerical data, if we take a clue from how chapter 6 went, so we have 1 sample proportion. Now we're going to talk about means. So we'll start with 1 sample means, and then 2 sample means, comparing those 2 averages, and then 3 or more sample means that we can compare. Right? And then that's it for inference. I know, it's crazy. confidence intervals and hypothesis testing for one sample mean. I'm going to do 7.2 and 7.3 on the same line because they're the same with slight variations. Confidence intervals and hypothesis testing for two sample means. And then 7.4 is hypothesis testing for 3+ means. There. Then we dip into regression, which is just lines of best fit. Feels completely different. You can still do inference if you want to. You know? So, might not feel like it now, but we are going to really settle down and just work on the same things over and over and over again now, which is why I love this part of the course. So we get to, okay, focus. Okay, let's see here. Oh yeah, but today, I'm just going to introduce some terminology, most of which we've seen before, so I'm just kind of introducing them in a new setting. And then next week, we'll start with confidence intervals, which we've already kind of seen. Right? Okay. Any questions before I zip down? Okay. So we're often interested in population parameters, right? I want to know what the population mean is or what the population proportion is, usually. Okay? And usually populations are difficult or often impossible to collect. Okay? And so we use these sample statistics as point estimates. Okay, so we've got these sample statistics, but a term that we haven't used yet that we'll see a lot of is point estimates. Point estimates are our best guess at the parameter. So if you're interested in the proportion of OC students who drive a black car, I can look out in the parking lot and I see black cars out there. So I am going to have some proportion, right? And so let's say maybe, I don't know. How's it looking? There's like shades, 2, 3, say 15%, right? That's a proportion. 15% of the cars in the parking lot are black. The rest are not black, right? Just lump them into just being not black, right? So then we can talk about that as a proportion, right? P hat, then my sample proportion would be 0.15. So point estimates is just our best guess from the sample. The problem is, even if I went out and I drove around with security and I counted how many black cars were in all the OC parking lots, if I did it in the morning, I would get a number, right? But even if I circled back and I did the whole loop again, I might get a different number, right? Because my sample changes, people come, people go, right? And so if I did it kind of 3 times a day, I would get different point estimates from each time that I collected a sample, right? That's okay, right? Sample statistics vary from sample to sample, okay? But if I told you that, okay, this morning I went out and I found 15% black cars in all our parking lots, and then later on 17%, you'd say, okay, little up, but still hovering around the same values. Then I went back out the next morning, 16%. You're saying, okay, that seems, on par with what you've been finding, right? And then, let's continue that 14%, 12%. Oh, that's low, right? And then I come back and there were 45% black cars in the parking lot. You sounded like someone reacted to my 45% perfectly. That's insane. That is not at all what I would expect. We're expecting something around 15%, right? And so, right, we're going to assign probabilities to that. So the probability of that is very, very low, right? Go back out there and count again. Or black cars are taking over. It's the other conclusion, right? But so sample statistics vary from sample to sample, okay? So that's okay, we can kind of handle that. The problem is we only get one sample, okay? And so kind of in the background, we have to imagine all these samples kind of taking place, right? But we only get one sample, okay? So quantifying how these sample statistics vary, okay? So assigning a spread to, right, the proportion that I'm collecting, right? I'm expecting variability, right? And so if we're able to quantify it, meaning if we can assign a number to it, right, some standard deviation perhaps, right, then we can estimate the margin of error. Now, the margin of error is a new term that we're introducing here. I think of it as a buffer. Okay. If we have a point estimate, that's my best guess. Okay. And then we'll have some margin of error that we add on to it, right? If we go back to this example, where was it? Here. Okay. We had a point estimate of 130. Okay. And then this 2 sigma is our buffer. We said, well, then I could move down a little and I can move up a little. And these distances are what we call our margin of error, right? Or I think of them kind of intuitively as a buffer where these are plausible, reasonable values, right, within this range. So it's some I'll say plus minus buffer that we can tack on to our point estimate, because we understand that if I went out and I collected a brand new sample, right, then it would be slightly different, right? But if I put on a buffer, right, or some margin of error, I should start calling it margin of error, then I can feel more confident in reporting my results, right? Another example, right? Before we go kind of assigning numbers to the variability, which is really just the spread, right, among these samples. Another example of how point estimates vary from sample to sample. So imagine this. Suppose we randomly sample 1,000 adults from each state in the US. Now, would you expect the sample means of their heights to be the same, somewhat different, or very different? We think about this, right? I collect 1,000 adults in Well, let's start with the states that I know. Washington, and I calculate the average. I'm not going to say what it is because I don't know what a reasonable average is, but that's just some number. Right? Then I go to Oregon and I collect a random sample of 1,000 adults and I calculate the average. Yeah. Then I go to California. Might be nice. Collect 1,000 adults, average height, right? And so now what I'm going to have is a sample filled with sample averages, right? That's kind of weird. So here, this becomes a sample of sample averages. These are just numbers, right? These are just numbers. You can make a histogram of them. They're numerical, right? So you can make a histogram and you would expect them to, or you might expect them to end up looking like this, and they would. Some states surely are shorter than others. Some states might be taller in general, right? But overall, they'd be centered on mu. Now, the mu is all adults in the entire US, right? So US adults. Now, of course, do you expect, so if there is some population mean for the entire US adults, which exists, but we could never think that we could calculate it, right? At the same time, every adult in the US reports their height at that moment. It's impossible. It exists, right? But we can't measure it. Now, do you expect all of these to be pretty close to this mean? Yeah, right? Once I'm taking into account that these are all averages, right? These averages are going to be really, really close. And so the spread, right, for these sample averages is going to be less than for individual data. But they'll still follow a normal distribution. What do we love about the normal distribution? We know how to find probabilities associated with the normal distribution. I'm sure there's other things you love about the normal distribution as well, but a huge perk is being able to find probabilities. I know you guys. You love the normal distribution. Well, here, the normal distribution, we're not done with it yet. It's going to haunt us in chapter 5, chapter 6, and a variation in chapter 7. Wow, lucky us. But it's nice because we've already gotten to know it, right, a little bit. So the normal distribution allows us to find probabilities. That's nice. As long as we have some mean and the spread. So we need to know how to find the spread. Okay. It's going to take us a little bit to get there, but we will get there. I will say this though. You can calculate the standard deviation of these averages, right? But then if you think about kind of how you'd have to say that is the standard deviation of the sample means. So instead of calling it the standard deviation of the sample means, we assign a new term called the standard error to it instead. So here, oops. The standard deviation of the sample means is called the standard error. Which we can abbreviate SE. This got tight here. Error. So what we'll see is that X bar, the distribution of X bars, will follow a normal distribution, and it will be centered on mu, the population mean, still. And it's going to have a standard deviation of the standard error of X bar, which I'm not. Fine, it's sigma over root n. So, but that's chapter 7 stuff. Or S over root n. For now, it's the standard error of the thing that we've collected. Now we're going to focus on proportions, but like I said, I find averages are a little bit easier to wrap our heads around, right, instead of proportions. But we start with proportions. But here, this was a quick example using averages. And I'll reintroduce all this, but I find I should say stuff probably like 7 times before I can expect you to actually hear me. So I say it a bunch. To me, I know, not to you. So here are some examples from articles and things like that you'll see, right? So as you kind of learn more about statistics, you'll start to see statistics everywhere, right? And become aware of it if you haven't already. Okay. I'm only going to read the highlighted parts because it's kind of long and ugh. And so a plurality of the public, 41%, believes young adults rather than middle-aged or older adults are having the toughest time in today's economy. So it sounds to me like they did some sort of survey and they asked, you know, which of these age categories do you think is having the hardest time? And 41% said that young adults are having the hardest time right now in today's economy. I'm curious to know when this was from, but probably still true. Then, skipping ahead, among all 18 to 34-year-olds, fully half, which I have beef with, because let's say nearly half, 49% isn't fully half. It's nearly half. Ugh. They love to get fancy. And I mean, having been the one to write these reports, it gets really boring. You just want to come up with some new words. I get it. But don't say fully half if it's only 49%. Right? Nearly half, 49%, say that they've taken a job that they didn't want just to pay the bills, with 24% saying they've taken an unpaid job to gain work experience. Now, this 41%, 49%, and 24%, those are all point estimates, right? They're all sample proportions. And so here, we're given some sample proportions. P hat is 0.41. That's the sample proportion of the public. Okay. Now, p hat equals 0.49. That's of the subgroup, right? Among all 18 to 34-year-olds. Yeah. And then same subgroup, we have a different proportion, right? Because this 49% refers to those who say they have taken a job they didn't want just to pay the bills. They said, yep, that's true. I have done that. And you probably should do that. You have to pay your bills. But 24% saying they've taken an unpaid job to gain work experience, another sample proportion, right? 24%. So another sample proportion. Now these are all from 18 to 34-year-olds, which means we can only use those as an estimate for the population of 18 to 34-year-olds, right? Whereas here, this was of the public, which means I can use that 41% or that sample proportion of 0.41 and learn about the public, right? So it depends on where your sample proportion came from, right? What you can infer to later on. So the margin of error is also going to be a percentage if the article is written in percentages, which it often is. We usually don't see articles reporting 0.24, a proportion of 0.49, right? Because most people don't want to read that much, right? But 49%, everyone just knows what that is, right? We have a better understanding of percentages. So usually in reports, we use percentages. But for math, right, doing calculations, we have to use the proportions. But it's easy enough to convert them. So the margin of error is going to be kind of the plus minus buffer, if you want to think of it that way. So we're told that the margin of sampling error is plus minus 2.9 percentage points for results based on the total sample, which I'll clarify is the public, and 4.4 percentage points, which means that there was more spread, right, than the public for the 18 to 34 years old. And here's our first real introduction at the 95% confidence level. For now, let's just kind of absorb that. I will say 95% confidence level is the default confidence level. This is our default confidence level. But I'm trying really hard to not say more than that. Good. So if we have an estimate for the public, right? So here's the p hat as a percentage for the public, plus minus the margin of error for the public, has to be for the same group, right? So 41% plus minus 2.9%. When you say it like that, you say, oh, okay, I've probably seen something like that before. What we can say then is that we are 95% confident that 38.1, which is 41 minus 2.9, to 43.9, of course, 41 plus 2.9, right? Down a little, up a little being 2.9 in this case. Of the public believe young adults rather than middle-aged or older adults are having the toughest time in today's economy, right? And what we're talking about here is where this 41% came from, right? So we have this point estimate plus minus some margin of error. And it'll be our job to calculate what the point estimate is and what the margin of error is. Okay, but for now, it's nice to have seen them in action already. Okay. Whereas the 49%, if we scroll up here, the 49% is referring to the proportion of 18 to 34-year-olds who say they've taken a job that they didn't want just to pay the bills. So now let's take that, lock it in. 49% plus minus the buffer, right, of 4.4% means that we're 95% confident that 44.6, so down 4.4, to 53.4, up 4.4% of 18 to 34-year-olds have taken a job they didn't want just to pay the bills. So if we think about this on a number line, we've got our point estimate of 49%, and then we went down 4.4, which put us at 44.6, and we went up 4.4, putting us at 53.4%. We've seen that last day. Right? So we have kind of done it, sort of. Right? Sneak previews. Okay. So here, I'll do these different colors. There. Why would we need the buffer? Right? Because this 49% came from the sample that we collected, right? So we collected some, or they collected some number of 18 to 34-year-olds. Doesn't say how many, I think. Right? But if we were to collect a brand new random sample of the same size, I would expect the percentage to be similar, but not exactly 49%, right? So we're expecting that similarity, but not exactly the same from sample to sample to sample. And so then that's where this kind of buffer range comes in, right? I would expect my sample proportions to be kind of in this range. Yeah. Suppose the proportion of American adults who support the expansion of solar energy is 0.88. Now, when we're told that P is the population proportion. So the difference here is we're pretending to know what the population looks like. And it's a really common way of kind of backtracking it and saying, hey, what if we just force the population proportion to be 0.88? We just say that we know that. And then what if we collect samples and see how they behave around 0.88, right? And then we'll know what the population or what the sample distribution looks like. I got ahead of myself, but let's, for now, pretend that we know the population proportion is 0.88. Okay? Is a randomly selected American adult more or less likely to support the expansion of solar energy? So now just knowing that for the entire population, 88% of them support the expansion, right? So you've randomly selected one person, and the probability of each person being in support, well, is 88%. So I feel like they would be more likely to support the expansion of solar energy, since the probability, right? Proportions, percentages, and probabilities are all the same, right? Is 88%. Yeah? So here, since the probability is 88%, right? Or percentage, but we can think of probabilities as percentages too. Now, oh, not yet. That's the slide I thought was coming up. What can we do when we live in a shoe? Suppose you don't have access to the typo galore here, population of all American adults, which of course is usually the scenario for most things, right? We don't have access to the population. But in order to estimate the proportion of American adults who support solar power expansion, what you can do is you can sample from the population and then use your sample proportion as your best guess for this population proportion. Right? You take a sample and say, hey, here's my best guess. Throw a little buffer on there, and then you feel 95% confident. Well, you've captured it. So, as a kind of a thought experiment, of course, if I asked each of you to sample with replacement 1,000 American adults, we can change it to Canadian. It would still be really difficult. Canadian adults, even BC adults, even kind of difficult for if we would boil down to Kelowna adults. That's still kind of hard. But it's a thought experiment. So you're going to sample with replacement 1,000 American adults from the population, right? So that means each of you goes out and collects a random sample of 1,000 American adults or Canadian adults or whatever population we choose. Okay? And then you ask them one question. Hey, can I just ask you one quick question? You'd be those guys on the street corners. Hey, can you just tell me how you feel about this? Do you support solar power or not expansion? I think solar power expansion or not. Yikes, it's riddled. Right? And so you would get, what would your data set look like? Every individual data set would have yes, yes, no, 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 yes, 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 no, 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 yes, 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 categorical data, right? So now, right, you would each have a sample of categorical data, yeses and nos. Usually we code our nos as zeros and yeses as ones. Okay? We code 0 equals no and 1 equals yes. Oops. Yes. I don't know why I put another S on there. There. Okay. Just shorthand. So you'd have 0, 0, 1, 1, 1, 1, 1. Right. Then you would find your sample proportion. How would you find your sample proportion? Here's our first introduction. We've seen p-hat, but I haven't told you how we get it, right? But if you have yeses and nos, right? Shorthand, we use a capital X over N, where capital X is the total successes. Yeah, so it's the number of successes, so number of yeses. Then what's nice about coding them as zeros and ones is you can just add up the whole column, right? The nos won't add anything, but the yeses will increase by 1 for each yes that you have, right? And so really it's going to be the sum of the ones, right? Or the sum of your column divided by however many we collected. Now we all individually collected 1,000 adults, right? And so our N would be 1,000 for all of us. Right? Now, if we plot the distribution of the sample proportions obtained by the members of the LAS, which should say class, there, then, right, we would have a sample proportion, a sample proportion, a sample proportion. Sample proportions are just numbers, right? In fact, they have to be numbers between 0 and 1. We know that about proportions and probabilities, right? And so now I have a collection or a sample of sample proportions. Yikes. Huh? But what we can do is we would find, yes, it's true. We would find that they plot and create another normal distribution. This thing won't leave us alone. That's nice though. Again, because we kind of know it. Even if you don't like the normal distribution, you should probably start liking it pretty soon. So I'm going to tell you this. Instead of being centered on the population mean, because now we're talking about proportions, it will be centered on the population proportion, which makes sense. If you kind of step back and think about it, if we know the population proportion is 0.88, right? And if you had to kind of make up numbers, it's not how we should do it, but if you had to make up numbers for what your individual sample proportions are, they would hover around 0.88, right? You might be below 0.88, you might be above 0.88, but they'll all be around 0.88, right? Some of you might be daring and put it down here, right? Ooh, 0.75 maybe. You're crazy, right? Oh, up here, 0.9. Fewer of you would dare to tell me, oh, 0.9. Say, really? Because I'm expecting it to be around 0.88, right? So it's allowed, but the probability is small, right? Because the area under the curve out here in the tails is small, making the probability of that happening very small, right? Okay. You can ignore this next slide, but don't worry. Ignore, see, well, you can't see the Excel assignment yet because it's not available. But I've created an elaborate Excel assignment to illustrate just this, where we pretend to know a sample proportion and then, or a population proportion, I should say, and then we generate many different samples. We look at what the distribution, so what the histogram of those sample proportions looks like. And then you guessed it, we calculate the standard deviation of those sample proportions. So don't worry about this slide. This is all R code, but we do kind of the same thing, but in Excel instead. Something to look forward to once it's back up and running. Okay, so there's one assignment from today's lecture, but not two, just one. I'll give you lots of time to do it though. So if you were to repeat this process, really what we're doing is a simulation, right? So when you hear the term simulation in statistics, it just means that we kind of invent a scenario and we run it many, many times. Okay? It's kind of a reasonably new invention because we didn't have computers before. And so it was just as tedious as you go out and collect a sample, you go out and collect a sample, you go out and collect a sample, and then we'll put them all together, right? That's tedious. Okay? Now with computers, we can just pretend it happened. Okay? So the simulation would look like this. Just like I said, that looks like a normal distribution to me, right? And we also happen to know that it's centered on 0.88 because it's referring to that earlier example of, hey, let's force the population proportion to be 0.88. Okay, nice. So this is what we call a sampling distribution. Any statistic that we calculate has a sampling distribution, okay, and it's been established, and the only ones that we, or the ones that we look at, have long ago been established. Okay? And so we don't need to do all that work, but all statistics that we see in this course, there are some that don't have any, but all statistics have a sampling distribution. Now, knowing the sampling distribution there helps us assign probabilities, right? Find probabilities. So that's what I mean. The probability chapter of the course is done. That's the one people don't like usually, but we're still going to work a lot with probabilities. We still find probabilities, but not in the same way, right? Oh, we already did this. I already drew it on the first slide, but what's the shape in the center? Well, the shape is normal or approximately normal. It looks symmetric and somewhat bell-shaped. I'll call it approximately normal. And centered roughly, or we happen to know that it's centered on 0.88. Wow, they're really dragging it out. The center is about 0.88. Yeah, I know. Said it. Huh? Here's the pickle. Sampling distributions are never observed, right? Unless you're inventing statistics, which we're not. That's been done. Okay. And so then I'm just going to tell you what the sampling distribution is, right? Hey, if you're collecting a sample proportion, p hat, well, then you're allowed to assume that it came from this distribution. It's going to be a normal distribution. It's going to be centered on p and have some spread. Oh, what a cliffhanger, I know. And so in real world applications, and for us in this course, we never actually observe the sampling distribution, right? But it is useful to always think of the point estimate as coming from this hypothetical distribution. And so understanding the sampling distribution is going to help us assign probabilities to an observation that we found, right? And kind of just in general, make sense of point estimates. Now, the sampling distribution is so important that it got just I think the most important sounding name of all, the central limit theorem. Okay? So the central limit theorem, or the CLT, central limit theorem, is basically all the work that early statisticians did to establish, hey, if I sample a sample mean, what does the distribution look like, right? If I do a sample proportion, right, then what does the distribution of sample proportions look like? What they found and what created the central limit theorem is that, let's start with sample proportions, but then in chapter 7 we'll see that there's a central limit theorem for means as well. But sample proportions will be nearly normally distributed with a mean equal to the population proportion P. So that much we've seen, right? We've seen that normal distribution take shape, and we saw that, okay, it is centered on P, which we kind of reverse engineered, right? We forced the population to have P 0.8. Then we saw that it was centered on P, right? Now here's the new part. The standard error. The standard error, remember from way earlier, is shorthand for the standard deviation of the sample proportions. Yeah? So the standard error is the standard deviation of the sample proportion. Oh, there's no bracket. Okay. This looks bad, but if we pick it apart, it's not so bad, right? There's a square root, yes. P, okay. P is the same as this P, the population proportion. 1 minus P, okay, you can do that, right? 1 minus 0.88, okay, we can handle that so far. N, well, that's your total sample size. Our total sample size earlier was 1,000, right? So we just get a nice number and then we take the square root of it, right? And that's going to be the spread. Has anyone figured out the problem yet? I'm going to tell you anyways. Even if you're not sure. Maybe you have. Because what's the problem? What's our overall goal? Why did we even collect p hat? We collected a sample proportion to try to learn about the population proportion. So I can't, if I don't know what p is, I can't really use it, right? But I have my best guess at what p is, and it has to be p hat. I have no other better guess, right? And so all we do is we replace it with p hat. And so I think that's on the next slide, but here, how do you read this? Seen this before. P hat follows a, right? This means follows a normal distribution with a mean of P and a standard error now of the square root of P times 1 minus P, which I usually write Q over N. So we have some mean and some standard deviation for our normal distribution. And so, right, that's why what we were finding earlier is that, yeah, it does look like a normal distribution, and it does look like it's centered on the population proportion. Now, like a lot of things in this course, I find, we will not go through a detailed proof of why that is the standard error, as long as you all agree that you accept it as true. You willing to do that? I hope so, because it's been a long time since I did the proof. And I feel like it's quite long. You can Google it. What you will see though is once we just accept this as fact. Accept as fact. Sometimes it's just how it is. But what you will see is that as your n increases, so here n is in the bottom, right, in the denominator. So as you're dividing by a bigger number, right, p and p stays the same. Okay, so as you divide by a bigger number, right, then this number gets smaller. Right? Taking the square root of a smaller number yields a smaller number. Right? And so as n increases, the standard error overall is going to be decreasing. Right? And so the reason for that is, right, because what's the standard error? The standard error is the spread. Right? And so as you increase your sample size, right, you're going to yield or get more consistent estimates, right, best guesses, because you've taken more of the population, right, into account. And so then you expect your spread around the population proportion to get tighter and tighter and tighter, right, as you increase your sample size. And so then your standard error is decreasing. Okay? And so the variability among the p hats will be lower. And this is the reason we want large samples or sample sizes. Right? Probably even heading into this course, you knew that, okay, you should probably have big sample sizes, right? Heard people talking, oh, yeah, but the sample size was really small, right? And so then makes you kind of wonder about the results. And so we have this intuitive knowledge about sample sizes already, right? So as long as you're prepared to accept this as fact, we can move on. Now, I want to take us to the formula sheet. There's the Poisson, which I posted that video assignment on, which you can't do, so don't worry. I'm not going to test you on the Poisson distribution. It's just another distribution, but it is fun to say, fun to do. And so you can look at it. It's got some lambdas in there. But what we're talking about right now is summarized at the top of the one sample proportion section of your formula sheet, right? Which is where we're going to spend all of chapter 5 and 6.1. So we're going to work through this last thing on the first page of your formula sheet, right? Nice and slowly. So here, I'm going to copy this and bring it in here. So here, this is the central limit theorem. And it is just theoretical. We don't really use it, but it's there for completeness, and that's what we're talking about right now. And so it says that p hat follows a normal distribution centered on p with a spread of the square root of pq over n. Remembering that I use q where q is 1 minus p. Save myself one keystroke, I guess, 2. 4 if you count the brackets. Anyways. So this is 5.1. And then on Tuesday, we'll do confidence intervals. And then, lucky us, a little bit bigger, 5.3. And then finally, 6.1. Introduce just a new thing. Okay? So it's going to take us time to work through just this little section. But today, we're hanging out here. Now, the normal distribution is a beautiful thing. We can all agree on that. But there are conditions that we need to check in order to make sure that it applies, right? And so the central limit theorem only works if some conditions are met. Yeah. I'll underline this here. So the conditions can be broken up into 2 subcategories: independence and sample size, or I often call it the normality condition, or just normality. So in order for us to assume that something follows a normal distribution, so here, this is really what we're checking for here. In order to assume a normal distribution, we need to check the conditions. Check the conditions. I'm going to call it conditions for inference, because I know in the practice questions and on the test, it'll say, okay, what are the conditions for inference? Okay. So that might be nice to start saying now, I guess. But we're checking the conditions. Okay. Conditions or assumptions. Yeah. Okay, so conditions or assumptions. Sometimes they're assumptions. We don't know. The independence category, there are 2 kind of subcategories that we have to check. Okay, but in general, what we're looking for is that the sampled observations must be independent of each other. And so this is difficult to verify, of course. We don't know anything about our sample observations, how they relate to each other, but it's more likely if we've randomly sampled, right? This is going to be the most important part. If you've collected a random sample, right, what we established even back in chapter 1 was the reason we collect a random sample is so that I can assume that all my individuals in my sample are independent of each other. Whether that's true or not, I'm allowed to assume that they are if I've randomly sampled. Okay. Now, I will say, if sampling without replacement, this one is confusing, so I usually ignore this one. I usually ignore this one, this condition. I'm going to tell you why I ignore it. What does n less than 10% of the population mean? It means that your sample size has to be less than 10% of the population. kind of going against our general rule of, okay, you want big samples, but not too big, right? Why not too big? Because if you've collected more than 10% of the population, the probability of people being dependent on each other, right, having siblings and kind of people from the same neighborhood or things like that, right, making dependent observations is higher, right? That's usually not a concern. We usually can't afford to sample more than 10% of the population. It's crazy, right? So it's not really something we need to worry about, right? And so that's why I ignore it, because it's kind of this counterintuitive rule that, yeah, you want big samples, but not too big, right? Just ignore that part. Take as big a sample as you can. I guarantee it, it's still going to be less than 10% of the population, right? So not something to worry about. Huh? So like I said, I usually ignore this condition because it'll never really be a problem. But it's good to be aware of, right? That it exists. So for the independence condition, really all I'm looking for is, well, does the question say that these people were randomly sampled? Usually it does. Right? Then you can assume independence. Right? Otherwise, what would you have to say? That's why I call them assumptions sometimes. I assume the sample was randomly selected. Therefore, independence is satisfied. Right? Either way, right? Whether it says or you have to assume it, right? That's how we get to the independence condition. The sample size, or what I prefer to call the normality condition, the sample size is more leading in terms of what you need to do for it, but the reason we want it is for the normality. It says that there should be at least 10 expected successes and at least 10 expected failures in the observed sample. I will say that, of course, this is difficult to verify if you don't know the population proportion, right? Or you can't assume a value for it. Yeah. So in those cases, which is pretty much all cases, we look for the number of observed successes and failures, and they have to be at least 10. That sounds familiar, but we didn't have very much time to do the normal approximation to the binomial, but it was the bonus on the test, right? So maybe you did, right? Where we had to have at least 10 expected successes and at least 10, observed successes and observed failures. I think, do I have it? Yeah. Then I won't write it here. So, but if we have at least 10 successes and at least 10 failures in our sample, then we can assume a normal distribution. We can just move ahead. Mute. I thought I had my pointer on here. So as we said, the central limit theorem says that, okay, the standard error, which will replace our standard deviation, right, is the square root of PQ over N. With the condition that NP and N times 1 minus P are at least 10. These are the expected successes, successes and failures are at least 10. However, we often don't know the value of P, which is the population proportion, which we're trying to learn about. So it feels weird to think that we would know it. In these cases, we substitute p hat for p, which means that the standard error of p hat is p hat times 1 minus p hat over n. P hat is a sample proportion. If you have a sample, you have a sample proportion. Right? Or p hat q hat. I know, wild and crazy. What do you think q hat is? 1 minus p hat. How about that for flexible shorthand, huh? Pretty good. And that means that our observed successes is n times p hat. If we also remember that p hat is x over n, the number of successes, right? This is a hat. If I multiply both sides by n times p hat is x, right? So being able to move around here, if you have the number of successes, which we usually do, right? 4 out of 5 dentists recommend, that's 4 successes out of a total of sample size of 5. Normality wouldn't apply because I need 10, right? But 40 out of 55 dentists recommend, I don't know what they recommend. Colgate, Crest. Those are Sensodyne, probably Sensodyne. They all love Sensodyne. Both my sister and my husband are dentists. Ask me if I floss. I don't. I know, it's really bad. Anyways, so the observed successes, if you have your n and your p hat, you'll have to calculate the successes, but often you'll be given the successes, the number of successes in your sample, or in your question, I should say. Either way, has to be more than 10. Be 10 or more. And your observed failures, you can calculate n times q hat, or if the question gives you n and x, well, if n is the total sample size and x is the number of successes, then n minus x must be the failures. And that has to be greater than or equal to 10. And this is for the normality condition or the sample size condition. So depending on the information that we have, right, these will be the same, n times p hat, if you have it, or if you have x, that's easier, right, already. So even though we didn't know what p is, we use our point estimate, our best guess at what p is, which is p hat, right, from our one sample. Suppose we have a population where the population proportion is 0.05. Okay? This is something relatively rare, right? 5% of the population. Okay? And so here, this is what we would call a rare outcome, right? Or relatively rare. So I have a low probability of seeing this. And what if we take a random sample of size 50 from this population? If we calculate the sample proportion in each sample and plot these proportions, then would you expect this distribution to be nearly normal? Okay. Now, from the normality condition here, if these are satisfied, right, both being greater than 10, then I would assume a normal distribution. If they're not satisfied, I cannot assume a normal distribution. And the reason is this. The success failure condition is not met. So if I take a sample of size 50 and I expect 5% of them to be successes, I would expect 2.5 successes. And so here, successes, oh, whoops, oh, just turn my E into a C. Expected successes is 2.5. That's too small. I need at least 10. Which makes sense. If I'm trying to capture a rare thing, I can't have a small sample size in order to try to do that, right? I understand that I need a bigger sample size to do that. So what we would find if we collected samples of size 50, right? I see that, okay, most of these here would be hanging out around 0.05, the sample proportion, but the distribution is not quite normal, right? We need to increase our sample size in order to get it to that normal distribution. So we can look at some examples of some simulations where we change our P from 0.1, 0.2, 0.5, 0.8, 0.9, right? Relatively rare outcomes to relatively common outcomes. What's the problem? I'm not only concerned with the successes, I'm also concerned with the failures, right? And so here, if P is 0.1, Q must be 0.9, right? If P is 0.2, Q must be 0.8. If P is 0.5, Q is 0.5. If P is 0.8, oops, Q is 0.2, and if P is 0.9, Q is 0.1. So they have this kind of, I don't know, teeter-totter relationship, right? But I need both my successes and my failures to be at least 10. So at each sample size of 10, 25, 50, 100, and 250, we start to see the normal distribution take shape. What you'll see is at these lower probabilities, as well as the higher probabilities, right? Because they're basically the same. Probability of success, probability of failure, probability of success, probability of failure, right? They're the same. Okay? They're just on different ends of the scale, right? So for these smaller probabilities, right, or I should say extreme probabilities, it takes a little bit longer to get to a normal distribution. So at a sample size of 10, it's really obvious that it's not normal. 25, it's kind of getting there, but not quite. At a sample size of 50, I'm feeling more comfortable with a normal distribution. Definitely at 100, I'm starting to call it a normal distribution, right? The closer you are to a 50-50 split, right, the smaller the population or the sample size you'll need, right? And so here, this will require, so a 0.5 split requires the smallest n. Right. What is my smallest n? If I have a 50-50 split, I only need a sample size of 20, right? 10 successes, 10 failures. Nice. That's a tiny sample size, 20. So here at 25, already it looks like a normal distribution. In fact, at 10, it kind of looks like a glitchy normal distribution already with a 50-50 split. When we said glitchy, right, what I really mean is more discrete. So when either NP or NQ is small, then the distribution is more discrete, more spaced out. If one of the two is less than 10, then we see quite a skewed distribution. Huh? And the larger they are, the more normal the distribution becomes. Huh? And so if they're both very large, then the discreteness or the glitchiness, as I called it, right, kind of smooths out and becomes smaller and smaller. Huh? And so then it starts to look more and more like a normal distribution. Don't worry, it's our last slide. So I'm losing my voice, so we'll call it there. But so what we're doing, right, using a sample statistic to estimate a parameter, right, is really common. And as I sort of sprinkled in the beginning, is that we can extend it to other statistics, right? Like the mean is really common. Huh? Take a random sample of students at a college and ask them how many extracurricular activities they're involved in to estimate the average number of extracurricular activities all students in this college are interested in, right? That would be a mean. And like I said, the mean also has a sampling distribution. There's a central limit theorem for the mean as well. And so, and if you flip the page on your formula sheet and you go down all the way to one sample mean, there it is. What a spoiler alert. I know. The mean follows a normal distribution, okay, centered on mu. We've seen that already, or we've kind of expected that already, with a spread, a standard error of sigma over root n. Fair enough? Okay. And so we'll see the same behavior for different scenarios for basically the rest of the course, or at least until test 2. Okay. And so these principles and the general ideas apply to other parameters. Even if the details change a little, you have to be a little bit patient. Huh? But with that, I leave you to the weekend. Hope you enjoy it. Enjoy some time off the assignments, and I'll send out an announcement when it's back up and running.